So let's get started with binary. And today we're going to talk about bits, bytes, and hex. First, let's look at how a computer would look at code. So generally, you write code you can understand, and you put characters on a file, say hello.java file, hello.c file, and then somehow the computer turns that into something that it can understand. It performs operations, and then it gives you something in return. It either prints, creates new calculations, makes something show up on the screen, so on. But all of that is done by turning what you write on a file into zeros and ones. So let's look at how a computer would do that. And we're going to take this example for the next few lessons, and we're going to try to dissect what happens at the lowest level. So first, the computer is going to take the first character on the first line, and our first line is called include stdio.h, which is really just an import statement to be able to print things out. So it takes the pound sign, which is ASCII 35, and it looks at its number representation. So it's ASCII representation. So in this case, it's number 35. So each character is going to, by the computer, be assigned a number. This one's 105, N is 110, C is 99, L is 108, U is 117, and so on. So each one of the characters is just going to have some number represented by it. And that's because computers don't really understand characters themselves. Characters are just something that shows up on a screen. Computers really understand numbers. So if we take, say, the next letter, which is going to be the representation of D, which is 100, we're going to take that number, and what we will do is we're going to then turn it into binary. We're going to convert it to binary. And by we, I mean the computer. The computer will turn it into binary. So the number 100, 1 followed by two zeros, is turned into binary, which looks like 1100100. Which, to make sense of it, we're going to have to go into how we represent numbers. So let's take a step back from looking at what the computer is doing to what we do, how we interpret a number. So generally, what you've learned in school, what you still use in, say, math class is base 10. You're going to have each digit, it's going to be able to represent up to 10 values. So each one of you can represent up to 10 different values by using just one digit in math class. That can be from 0 all the way ranging up to 9. If we wanted to interpret, say, use or represent the value of 10, we would have to use two different digits. So we'd use the number 1 and the number 0, which means that computers use something called base 10. So, or sorry, base 2. Base 2 is only able to use two digits. So it's only able to represent two values per digit. Now, what does that mean in practice? So when we create a number, say in base 10, we'll take the number 145,609. Each one of those digits represents a value from 0 to 9. So you can't use more, let's say in the ones place right now, you can't use a 10 in there. You have to use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's it. If you want to do a 10, you're going to have to create a new digit, and you're going to have two digits. So in this case, if we look at base 10, each digit is going to represent some value that is a multiple of 10. So the digit 9 in this case is going to represent a 1. So that's the 1's value. Then the digit 0 is going to represent the 10's value. So we don't have anything in the 10's value. And then the digit 6 is going to represent the 100's value, and so on. So as we continue to add, each one of these is worth more than the previous one, but you're still just using one digit to represent that. So we just know that intuitively now. But in binary, you do a little bit different. what you're going to do is, again, you can only have 0 or 1. You can't go up to, the next digit that we use in base 10. And each one of these places is worth, in a sense, different values. So instead of going from the ones place to the 10th place to the 100th place, we're going to go 1, 2, 4, 8, 16, 32, and 64. But now we have two representations going on. And things can get confusing as you start using these representations. So we're going to have to differ from them. We're going to use base 10 and base 2, and we'll call those two different things. Now, if we take this value, 1100100, and we try to figure out what the base 10 representation of that is, we're going to only look at the places that have a 1 on them. So we're going to take 64, the 64 plus 32 plus 4, and we're going to end up with a base 10 value of 100. So 1100100 is the same in binary as 100 in base 10. Moving forward, we're going to use this notation to know when we're talking about binary and when we're talking about base 10. So there's going to be a subscript of 10 for a value that is base 10 and a subscript of 2 for a value that is binary. Having seen representations now, and we've sort of started understanding what bytes and what binary sort of is, we're going to look at what 1 byte equals in bits. So each one of these numbers that you've seen before, the red numbers in this case that have a subscript of 2, each one of those is a bit. We'll call those a bit. So right now on the screen we have 7 bits. We have 7 zeros and ones. So 8 bits equals 1 byte. And this is generally the notation, the name that we've given this amount of bits. And it might seem random, but that's because there's some historical background to it. When computers first started appearing and being created, they were created using English. So at the time, to be able to represent any English character, we only needed 255 values. So there was only 255 characters. The character A, the character B, the character C, / punctuation, so on. You could represent all of those with 255 values. So we discovered that if we used 8 bits, we could then get to that number, which is 255. So how do we do that? Well, if every single bit is turned on in 8 bits, what's going to happen is that we have a base 10 value of 255. So as we're looking here, each one of these bits, if we add up all of the base 10 representations for each one, we're going to end up with 255 base 10. So there you go. If we have 8 bits, we can represent every character we needed at the time, and we can then use bytes as a measurement of data instead of just bits. And what happens is that 8 becomes a really nice number for memory, and we're going to look at that in the future. So we can use 8 for a lot of different purposes, and it has a lot of advantages when it comes to reading things. You can read chunks really quickly. It's much easier to read a chunk of numbers than to read one number at a time. So for now, we'll just accept that instead of just calling it bits, we're going to use bytes a lot of the time. And many times when you talk about data, say your hard drive has 256 gigabytes. Well, that means that it's able to store that many bytes. So it's able to store that much data, which is a huge amount of data now. But there's another representation. This representation is called hex. Now, we're going to talk a little bit about why hex exists and why it's around and how it goes back to everything that we've looked at so far. But let's start by agreeing that hex is a representation that uses base 16. So one digit in hex is able to represent 16 values. And we're going to use the subscript 16 to be able to let you know that that digit represents a hex value, not a base 10 value or a binary value. But why do we use A, B, C, D, E, F? It becomes kind of unintuitive if you start mixing letters that way. Well, it goes back sort of how we represent numbers, right? So let's look at the start. So if we're just going to use one digit to represent 16 values, we can start at 0. And the corresponding value for the base 10 for that would be 0, and the corresponding binary would be 0, 0, 0, 0, 4 zeros. And then we go to hex 1, corresponding representations, hex 2, corresponding representations, hex 3, 4, 5, and 6. Still no problem, still able to just use one digit. 7, 8, and 9, again, pretty straightforward. So remember, it goes from 9 to A. What happens there? Well, imagine that we went from 9 to 10. Well, now we're using two digits for hex 16 or for base 16. We can't. We said that one digit was going to represent 16 values. Now we're using two digits. We're using the digit 1 and we're using the digit 0. So we can't do that. So instead of using 1 and 0, or as we generally call it 10, we're going to use A. Now we only have one digit that represents that amount of data. Now in base 10, it would be 10. And then in binary, it would be 1010. Now notice how confusing it starts getting if you use a 1 and a 0 to represent base 10. It looks very similar to binary, so we have to be careful about how we subscript, so we know that we're not talking about the binary representation 1, 0, but instead the base 10 representation of 1 and 0. And then we go on to the next hex, B, C, D, E, and F. So now that we sort of have agreed that we need these letters to be able to represent 16 values, we go, well, what's that number 16? Why would we go 16? Like what's the correlation between that? Well, we're able to represent 16 values with 4 digits in binary. So if we wanted to represent 1 byte, we can use 2 hex digits because 1 hex represents 0 to 15, which is 16 values. 4 digits in binary represent 0 to 15. So if we combine 2 hex, then we can represent 8 digits in binary, which ends up being 8 bits or 1 byte. So 2 hex is now 1 byte. Then you go, okay, fine, sure. That makes sense, but why? What's the point of doing that? Well, let's take this base 10 representation of this really huge number. Back in the golden days, when you wanted to write code, it wasn't as easy to just write source code like we can right now, like I showed you at the beginning of the video. Instead, you had to write it out by binary. Eventually we said, you know what, this is really tedious to do these zeros and ones because that's all the computer understands. And this is what it would look like for this one really big number if that's the calculation that we wanted to do at the time. So we said there's got to be a better way to shorten this. Again, we can't use base 10 representation because it's not a power of 2 in a sense. 2, 4, 6, 8, 16. And that's how computers naturally operate in powers of 2. So instead, we have to find some other way to represent this. So what we're going to do is we're going to turn this binary into some hex digit. Now, the hex digit is now much shorter. and we're able to represent that better. And we can represent really huge numbers with less digits if we use hex. How do we convert binary to hex? Well, we just take 4 bits per hex digit, and we notice that if we go through, each one of these 4 chunks is going to represent one of the digits in hex. And if we keep going, we're going to build this hex digit. And what we're able to represent is, in this case, 32 bits in less amount of digits, which helps a lot when you're writing code. In the future, we're going to look at how hex helps us write machine language, and we're also going to look at how binary can be used to be operated on so that we can create meaning to some of these numbers.